Hi, today I'll clearly explain how dynamic programming works using the famous 0/1 knapsack problem. I'll explain this with two examples in different styles. First, with a basic example that includes a detailed explanation, and second, in a fun, superhero-style scenario for practice. Imagine you have a knapsack with limited space. Let's say it has a weight limit. You have several items, and each item has two characteristics: weight and value. The goal is simple. Pick items to maximize the total value without exceeding your weight limit. Each item can either be picked or left out. That's why we call it the 0/1 knapsack problem. Let's dive into the explanation. We'll use 5 items, and the knapsack capacity will be 7. The rows in this table represent items, and the columns represent the knapsack capacity. How we solve this knapsack problem is by considering each item one by one, then figuring out the best possible value we can achieve for each capacity. Let's start. Here's the key concept. What we want to do for each cell is figure out whether we should include the current item or not by comparing two options, then choosing the bigger value. Option 1 is to not include the item. Keep the current best value, which means taking the value from the cell above. Option 2 is to include the item. Take the current item's value plus the best achievable value from the remaining capacity. I know this sounds complicated, but I'll show you exactly how this works. Item 1 has weight 1, which doesn't fit in capacity 0, so we put 0. For capacity 1, we have enough room to fit item 1, so let's compare our options. Notice the two arrows pointing to the current cell. The blue arrow shows option 1, keep the current best value, taking the value from above, which is 0. The red arrow shows option 2, include current item. For option 2, we take item 1's value, which is 3, plus the best value we could achieve with the remaining capacity. To find that value, we look at the cell in the row above, shifted left by the item's weight. In this case, it's the cell at position 0, where red arrow comes from. So we compare. 0 versus 3 plus 0 equals 3. Since 3 is bigger, we choose 3. The rest of this row continues to have 3. Item 2 won't fit in capacity 0, so we take the value from above to keep the current best value. For capacity 1, item 2 still won't fit, so we keep the current value. Let me pause here for a quick explanation. Why do we get the value from above? Because the cell above represents the current best value for the capacity. For example, our current location represents the case when we have 2 items available and knapsack capacity is 1. The best combination is still just taking item 1. For capacity 2, there's room for the current item. Let's compare the current item's value plus the value from one row above, shifted left by the item's weight, versus just keeping the existing value. Since 3 is bigger, we keep the value from above. For capacity 3, including the current item is bigger, so we choose to include. Then value became 5. The rest of the row continues with 5. Capacity 0 gets value from above. For capacity 1, we also get the value from above since item 3 won't fit. For capacity 2, there's room for the current item, and it gives us a better value than the current best value, so we put the current item's value. For capacity 3, item 3 improves the current best value, so we include the current item value plus the value one row above, shifted left by the current item's weight. The reason we shift left by the current item's weight is that we need to find the best combination that fits in the remaining space after taking the current item. To clarify this, the current position represents the case where we have 3 items, and knapsack capacity is 3. If I want to include the current item with weight 2, the remaining capacity is 1. So we need to look at the best value for when the knapsack capacity is 1. This is why we need to shift to the left by the current item weight in the row above. For capacity 4, nothing changes, so the value stays 7. For capacity 5, the value is improved to 9. The rest of the row continues with 9. For the last 2 rows, I'll show you an animation. There's no voiceover, so watch carefully. Now the table is filled. The maximum value we can put in the bag is 12. This is how dynamic programming works for the knapsack problem. If you understand this, try to solve the next example. For this example, I won't go over the details of dynamic programming again. Use this example to confirm whether you understood the concept, and let's have some fun. Let's say you're Nick Fury assembling the strongest Avengers team possible, but you have a limited budget. Each superhero has two characteristics: their strength and their cost. Your mission is to maximize the total strength of your team without exceeding your budget. Let's start solving this problem. Deadpool costs 2, so we keep the current best value for budget 0 and 1. For budget 2, we have room to hire Deadpool, so we compare don't hire, which gives us 0, versus hire Deadpool, which gives us 4 plus 0. Since 4 is bigger, we write 4. If you don't understand why I added 0, check the first example. The rest of the row continues with 4. Now we have Iron Man as an option too. We write 0 when the budget is 0. For budget 1, there's room to hire Iron Man, and since the current best value is 0, we write Iron Man's value. For budget 2, if we compare the current best value with the value from hiring Iron Man, the current best value is bigger, so we don't hire Iron Man. Here's the important reminder. Notice that the red arrow also increases as we move right. As I explained in the first example, the blue arrow represents the current best value, and the red arrow represents hiring the current hero. We compare the red arrow and the blue arrow, then choose the bigger one. With this rule, we can get 7 for budget 3. The rest of the row continues with 7. Start with 0. Captain America costs 3, so for budgets 1 and 2, we keep the current best value. For budget 3, there is room to hire Captain America. However, the current best value is bigger, so we keep current best value, which is 7. Same as 4 and 5. For budget 6, we can update to 9, including Captain America. Keep 9 for budget 7 too. For the last 2 rows, I will show you an animation. There is no voiceover, so watch carefully. Now the table is filled. The maximum strength for this team is 11. This is how dynamic programming works for the knapsack problem. As you can see, this algorithm can be used in different situations, whether you're packing a bag or assembling a superhero team. Thank you for watching.